All right, so, my God, this class has a lot in it. This class is like every math class here put into one semester. Because we're just about to talk about geometry. And we're going to actually define a geometry today, but to understand what a geometry is, you also have to understand something from abstract algebra. So our abstract algebra class is a whole semester of stuff. I'm going to try to get it in 5 or 10 minutes. just the important stuff. And honestly, I think you can all get this, even if you haven't had abstract. And then when you get to abstract, you'll have a new example to do. I found out also, for those who will be taking real analysis in the future, I'm teaching that next spring. So if you're planning, I know, I'm sorry. We could fail you. You want to fail out and then come back? No. It's such a generous offer. It's a very kind. Yeah. Oh no. Oh no. Let's not say anymore on video. Okay. All right. So, what is a geometry in week 10 of modern geometry? Fun story about grad school, it just came to mind. I took a class in differential geometry with one of the senior professors at CSU, Dr. Jaak Wilms. He was Estonian, had this amazing Estonian accent and hilariously dry sense of humor. It was me and 4 other grad students, and it was kind of an independent study. And I don't think any of us did shit the whole semester. And he didn't ask shit of us, so we did not do it. So we had our final at a brew pub in Fort Collins. Very nice. He was buying pitchers. So we had pitchers of beer in front of us. I was just hammered. And he's like, okay, so we should do something with the class. So, who can tell me what is differential geometry? And we're all like, because the beer, but also because we didn't know. We all got A's. That's grad school. We all got, I think he was like, maybe I haven't done my job in some way. So he's like, I better just give them all A's. When you go to grad school, if you go to grad school in math, you will get A's. You will get all A's. If you get a B in grad school, that's like, what are you doing? What are you doing here? So you'll probably get straight A's. And drunk. really, really drunk. Okay, what is a geometry? It's 2 things put together. It is a combination of a space where things live, triangles, circles, lines, stuffs that people do geometry with. A space where figures, and I'm just going to go ahead and define that, figures live. And this is the space we can think is probably going to be the complex plane for us, or maybe the extended complex plane. For us, this is going to be the space. But just think the plane. This whole class is really the plane. So this here is just the plane for us. You could go to 3-dimensional and then everything becomes, you can just imagine how insane that becomes. A space where figures live. Figures are subsets of the plane. Subsets of the space, I'll say it more generally. So, squares, lines, triangles, circles, geometry stuff, geometry critters. All the things you would do that you've ever done in geometry, the shapes. It's just the shapes we work with. So you've got a space where things happen. And then you've got a way in which they can happen. And that's the second part. A set of rules for how things can move about in the plane. A group of transformations. I underlined the word group because that is a technical mathematical. Hi, yay, you are here.
I got sprayed with water.
Oh God, what?
The car.
Are you serious?
Yeah. So then I turned around and I was like, I'm not going to class. And then I was like, okay,
Hey, wait, Cody, wait, give me your hand. Thank you. I'm so glad you're here.
oh, I'm cold now.
Yeah, I noticed, like, your hand is freezing. My God, do you need a jacket? I got like a jacket you could put on.
Yeah, it's okay.
Okay, all right. And I'm so glad you're here, though. We predicted you wouldn't be because you weren't in the earlier class. No, not like we're tracking you or stalking you. Just keeping tabs. Just keeping close tabs on your motions. So a group. Speaking of motions, a group of transformations that act on the space. What do I mean by a group? A group of transformations is a set. First off, it's a set of transformations. It's a collection of transformations, but much more. So it's just, rotations. All the various rotations might be in this set, or translations, or inversions maybe would be in this set. So it's a set of transformations. Let's call that T, fancy T. Use your own fancy T. Two, containing, I'm going to put three things here. A, an identity transformation. I think we call this let's just call this, I don't know what they call it in the book. I think I might have written it down here. Let's just, an identity transformation. What do I mean by that? It takes a Z and spits out a Z. So it doesn't change the things that it's acting on. So it doesn't change the space. Literally, this is one right here. This one's going to be the identity transformation for lots of different collections of transformations. Part B is the composition of any two transformations from T, fancy T, is also in T. So it is closed under composition. That's a slick way to say that. Closed under composition. And what do I mean by that? Let me be more precise about what I mean here. Let's be mathy about it. If S and not fancy T are in fancy T, the set, then so is, how about we just say S composed with T is also in that set. Let's keep it mathy. Does this statement look okay? can I clarify anything there? Does it need any clarification, any of this? Because I got one more thing to look for. So as I scan for subtle clues to see how things are going. We're good? Okay, I saw a nod. Yeah, see subtle nods. Okay, cool. All right. And then the last one. 3. That containing there, or containing, or that's not quite right. That makes sense with part A, but let's see, containing, or having, containing, having property. Maybe it makes it a little bit better, flow-wise. And then C, this third thing, if T is in the collection, the fancy collection, then its inverse is in there. If I can do something, if this collection allows me to do something to the plane, I can undo it. Let's just write that out, that's nice. Anything the collection allows us to do to the space, the space can be undone. So again, you might want to think these are our rules for transforming things. And today we're just going to really hang out with these ideas and look at things that are this and things that aren't this and think about them together. That's it. So, a geometry, I'm gonna say this in a slicker way again. Same thing, but I want to be a little slicker. Is a pair. I'm being more mathy as we move through. And we're gonna call it S and T. That's not a fancy S, that's my space. Where S is a space and T is a group of transformations. I've literally said this already, but not quite as mathily. This is the slick way. This is how you should remember it when the quiz comes. Eventually, and the quiz says, what is a geometry? You have to remember that. There you go. And then when I say, what is a group of transformations, you can give those 3 things. Identity, closure, and inverses. So when this group, just in your mind, identity, closure, inverses. Who's had abstract? I know some people are graduating, so they definitely had abstract. You remember this stuff? Oh God, I hope so, because it's the only thing you probably should have walked away with is the definition of this. I'll stop and let you get caught up. I would say, would you please read this chapter? This is section, so there's little details and words and stuff that I won't say, and I'll say it my own way. Bless you. So if you could just please read 4:1. And I know you're getting ready for your quiz, so this probably won't happen until after Wednesday. But please read 4:1. I'm not going to assign any homework until after that quiz is dealt with. I want you to focus on that. All right, so example time and non-example time. 2 ways to understand math, with examples of things and non-examples, right? And sometimes the things that are non-examples, counter-examples, help us understand the thing better. To know what something is something, is like, that's a good thing, but to know what it isn't is just as powerful, maybe sometimes more. Can I erase that right side? Is anybody still writing? No, okay, cool. All right, let's look at some geometries. And you're gonna start seeing some familiar things from this class and before. Just things that you knew were geometries, like what you thought geometry was before this class. That's still geometry, but it's just a geometry. So, examples and non-examples. We're gonna actually do a few problems to find the non-examples. Let's start off really chill. Chillest thing in the world is to take a shape in the plane. So I want to describe the geometry where I can take this triangle, good old 3, 4, 5 triangle, and just move it around. I want to be able to just translate things in the plane. The most basic thing, move it, just slide it around. No rotation in this geometry. This is called the translational geometry, is our first example. Super basic. The translational geometry. So our space S is the complex plane. We're not going to worry about infinity. We're not going to add infinity to stuff and just throw everything to the top of the sphere. Just good old, nice, normal plane. And our collection tau is a set of transformations. We're going to say T sub B of Z. This is kind of the index that tells us which of the transformations we have. T of Z just says take a number and add this constant B to us. So you can think of that as the constant also. And this is where B is just a complex number. So in other words, this is translate by B. So if B is this complex number right here, with each point in the plane, there's a transformation that translates by that much. So this B right here is take any other point Z and just move by that vector. You can think of that B as a vector, like that, and just translate by B. So it gives us a direction. There's Z plus B. Let's just talk about why this is a geometry. Does that make sense? Yeah? Okay. Cool. Simple, just start chill. So let's just convince ourselves this is a geometry, which essentially comes down to convincing ourselves that this is a group. So that's, if you've done abstract, this probably is pretty easy. But if you haven't seen something probably done this, it's almost like proving 1 + 1 is 2 in some ways. But let's do it together. So we've got a space. You're never going to have to prove it's a space. It's just going to be a space. It's just going to be the freaking plane, probably. We're not going to get much weirder than that. Ooh, let's take this guy though. Let's take this figure and translate it by B. If I just took this transformation, if this is a figure A, then T of A is just translate everything in this by B. Which kind of looks cool. It looks starting to look 3D and stuff. 3, 4. You probably don't label the sides. That starts to get a little messy. But this is T of A, T sub B of A. I should have used color. That looks shitty. But, I hope it makes sense. If it doesn't, let me know. All right, so to show that S tau is a geometry, we need to show, and this is what you will always need to show, that tau is a group of transformations. So step one is, what is the identity transformation? Would you just take a minute on this? And if you actually get done with that really fast, what I need to know is, what is the identity? What does it look like? Don't say it out loud, because I want everybody to think about it. What is the identity transformation? Then, how do I know this is closed under composition? And then what is inverse of a particular T sub B? So step one is, what's the identity? Step two is show that two transformations from here composed in sequence give you something from here. And then find the identity for any arbitrary T sub B. So I'll put these questions up here. Show that T sub A composed with T sub B is a translation. And 3 is find T sub B inverse. These are getting very abstract. Olivia, I'm trying to find anything in this bag that might make you feel better. I don't know what it is. I got something.
It's okay.
I know it is okay. I know I didn't splash you. I'm a nurturer. Did you know this about me? Did you want this?
Yeah.
There you go.
So cute.
It's that. It's really good too. Those are awesome.
Yeah, I have like the big kind.
You've had the big kind, yeah. I've never seen those little ones. Just to make sure we're all rolling on the same page. Mixing terribly mixed metaphors. Ella, have you found the identity? What does the identity look like here?
I'm kind of scared because it's just a guess.
Cool, no worries. It's gonna look like this for some B. What B do we pick that just doesn't change anything?
0.
Perfect. Was
So
that, yeah.
I just wrote T of Z equals Z.
I love
T
it.
of B of Z is Z.
Yeah, exactly. Yeah, that's beautiful. You expressed it perfectly. We could also use that notation we set up. So this is our identity. Just to be really explicit and to fall back on the notation we've already set up, make it things a little richer. Does that make sense to everybody? Why that's the identity? It just doesn't change anything. It's translation by nothing. And that's definitely in there because 0 is a complex number.
Sure.
Cool, let's just do part 2 together. Sorry, and I know folks are still working, and keep working if you want, it's all good, this is all on video. So I'm gonna set us up here, Kitra. I'm just gonna say this, take 2 transformations from T, and they each look like this. What do I do next?
So you want to write their composed equations.
Okay, cool, so let's put each of these up here so that we actually remember what, just make it clear to our reader what they have. So like so. So then what should I write?
So then you're going to compose them with the equations of T of TA of TB
Cool. So like that, and then of Z
equals.
equals, yeah, what do I write next?
So then it would be Z plus B plus A.
Let's go slower. Absolutely true. Let's first write out this, just to be, a little bit more refined. But you just jumped right to the end. So then, what would this equal? Where would you go with this one? There's like 2 ways you could go.
So you could put TB of Z plus A
I love it.
to substitute it into the equation.
Thank you. So that's beautiful. So just TB of Z plus A is that, love it, and then
Substitute the equation.
exactly. And then this is just Z plus B plus A.
And if A and B are both complex numbers, which we said they are because of the rules,
Yeah.
then it just makes another complex number.
That's just lovely. Thank you, friend. So what would I write in terms of the T notation? What is this actually? T. Which T is this out of the collection? Because I want to show it's back in there. Let's be really precise with our notation. This is what?
Like what subscript we'd write?
Yeah, what subscript?
Would it just be AB?
A plus B.
A plus B.
Yeah, exactly. Yeah, thanks. Yeah. So the composition of TA and TB is just T of A plus B. To translate by B first, then A is the same thing as translating by A plus B. I'm going to write that out. That's what you want to. You want to be able to move back and forth with the notation and the understanding. So, if we first translate by B, then by A, this is just translation by their sum. Very nice. And I've got to be more precise. And like Kittredge was more precise than I was. And since A and B are complex numbers, so is A plus B. Yeah, that's a really good, important detail to put in there. And we got one last thing. Camila, do you have that last, how do you feel about that inverse thing?
I don't quite.
Not quite there, okay,
No.
cool, no worries. My friend. Yeah.
Well, I got inverse of T of B would just be Z minus B.
Yeah, nice, it's cool, so, nice. So Christian is saying we've got T of sub B of Z inverse, I'll just use that just to make it really clear. The inverse of that thing. Yeah. No, let's put him here. Let's put him up there. Sorry about that. Is just Z minus B. And we can kind of see that from down here, because if you want the composition of these two things to be T sub 0 of Z, which is our identity, then A and B have to be opposites of each other to get you 0. So additive opposites of each other. This you could just say. I don't know what else you'd do to do other than what you did. Write it out. Does this make sense? That to undo translation by B, I just translate by minus B. So to undo, let's write that out. Translation by B, translate by minus B. And with that same little caveat that Kitra added, if B is a complex number, so is minus B. We didn't make it something that isn't a complex, we didn't make a new number. I put in a minus in front. Sweet. Let's do, so that's the translational geometry. Let's add a new term in here. Is it okay if I erase the left side of the board? Are Vivian still going over here? No. Okay, cool. We good on left? Okay. So what does it mean to be congruent in a geometry? You know, side angle, all that stuff, congruent triangles, similar triangles. Now we're taking that idea and generalizing it. That's just a way to determine if two things, my voice is changing, to determine if two figures are congruent. So definition. Two figures, A and B, are congruent in a geometry. So in geometry, S tau. Remember, this just means they're just points in S. So two figures. This just means I've got an A here, and then maybe a B over here. I'm gonna do something a little bit wonky here. Let's leave this example up. Let's make that B, make that 3, 4, 5. So I want A to be this triangle with the point this way, and I want B to be that triangle. And I want these sides to actually be labeled exactly as they are. That 3 is the vertical, the 4 is the horizontal arm, and then 5 is our hypotenuse. So that's figure A, that's figure B. We'll come back to it. These are two figures. They are congruent in our geometry if we can find a transformation that takes one to the other, but it's got to come from our restricted set of transformations. Transformation T in our group of rules, we can find a rule, a legit way to move things around so that T of A lands us on B. So that is congruent is the thing I'm trying to define here. I'll double it. I'm not trying to define two figures A and B. Just need a rule that lets me turn one into the other. That's all that means. Very mathified, very fancified. So here's two figures, A and B, that I made a big deal about. Are these congruent in the translational geometry? No. You want to say a little more, Lou? Just definitely right.
No, there's no way to simply shift it to like make them equal.
Yeah, there's something else going on here. To get from here to here, what do I actually need to do? Yeah, Nathan, yeah, what was that? Oh, love that. Flip it. So this actually would require not just a translation, but an inversion around a line. We would have to invert over a line to get that. That's a lot. So these two things are not equivalent. They are not congruent in the translational geometry. Not congruent in the translational geometry. That's the only one we've defined. Let's add another one in to our vocabulary. Translational geometry. Let's actually make that note to requires an inversion. This translational geometry is super rudimentary, just weird and very basic, like almost the most basic geometry in the world. The next most basic one's the one you had in high school. That's the Euclidean geometry, which is just a kind of a geometry. So let's get that up here. The Euclidean geometry, so that we can actually address another thing that these aren't equivalent in. Euclidean geometry it's really easy to define these things. First off, our space is just the complex plane. It's just the plane, planar geometry. Got my ruler, got my compass, splitting angles and shit. Euclidean geometry has a normal space, the plane. But our transformation group is the set of all transformations that look like this. E to the I theta z plus b. And here, theta is a real number, and b is a complex number. Ooh, almost wrote integer. So take a minute. In your head, you're tutoring someone in this class. What do you tell them this allows? I know it sounds terrifying to like say, think you're tutoring someone in this class, right? Like that sounds like I need a tutor in this class, so you could tutor me. I did at one point. He didn't respond, so I had to learn the shit on my own. So like, just think to yourself, what can you do in this geometry? What are the legit moves that a person can take? Ella, yeah.
You can scale it by z.
So the z is the thing that's going to come in to be transformed.
Okay.
The z is. So, but I am multiplying it by something. Is that a scalar? Is that dilation? Remember how we've got this?
Mm-hmm.
Which,
That's how I was thinking of it.
yeah,
It's not
beautiful.
an R.
There's no r, right?
Yeah.
So the r
So
is
you can
1.
just rotate and translate.
Just rotate and translate. Exactly. So this Euclidean geometry is just rotations and translations. That's it. So this allows translations and rotations. That's it. No flipping yet. Still can't invert. Inversion still requires some idea of infinity. Because what are you going to do with 0? You got to send it somewhere. So this is Euclidean geometry. Are figures A and B equivalent in Euclidean geometry? And the answer is no. You cannot rotate. Try. You cannot rotate that one and translate it into that one. If I rotate this guy, the best I could do is, right? I can rotate, and then I've got 4, 3, 5 like that. Did I do that right? Yeah, I think so. Is that a 180 rotation? Yeah, yes, ma'am.
Maybe I'm just confused, but I thought that reflections were a part of Euclidean geometry.
They are not.
Interesting.
It is, isn't it? I learned that too. They are not. Yeah. That's a fancier geometry that we will talk about because we've been spent like half our lives inverting things. So yeah, not yet. So figures A and B are not congruent in Euclidean geometry. And now I have to talk about the fourth dimension. Because I just have to whenever I get the chance. So these two figures are not equivalent in Euclidean geometry, the basics. And what also I found weird is Euclidean geometry doesn't include scaling. So there's something else. That geometry in high school is a little bit, it's not exactly this geometry, right? Because congruent triangles can be scaled versions of each other. So there's something else going on there. But this triangle and this triangle, so A is equivalent to C here. A is congruent to C. Nothing's happening. But it is not congruent to B. So let's just think in the world we live in. Does anybody have gloves with them today? No. No one has gloves. No one has a pair of gloves. Okay, that's okay. Imagine gloves. So I've got a right-handed glove and a left-handed glove. Right here, yeah? Praise the gloves. I got them right here. This glove cannot be moved into this glove. You can't turn a right-handed glove into a left-handed glove. That's why it sucks to lose a glove, right? You can't put your right glove on your left hand. It just doesn't work unless you turn it inside out. I guess there's that. That's the same thing we have going on with these triangles. What did it actually require to get this triangle here? It requires another dimension. I have to pick that sucker up out of the plane and flip it and bring it back down. So imagine, so we got three-dimensional space. Imagine we had another direction we could move in besides left, right, backwards, forwards, up, down. None of those translations are going to turn that glove into that glove. I need to somehow flip it, and even flipping it in 3D doesn't turn it in to this glove because the fingers bend like this. So what I need is a fourth dimension. So to turn if you lose your one glove, you can turn it into the other glove. It still doesn't give you two gloves. You take this glove, you lift it into the fourth dimension, wherever that is. I can't show you. Anything I show you will be a lie and misleading. Lift that into the fourth dimension, turn it over, bring it back down, you got yourself the other glove. But it requires another dimension. Inversion is actually somehow involving another dimension, right? There's flipping, there's a lifting, and a placing down. So that's one of my favorite 4D facts. Can't get you excited with finger waving. All right, let's see. We're gonna let out a little early today because of snow and stuff. And Olivia's got to go dry out somewhere. You know what? Do me a favor and read when you get a chance, but mostly get ready for the quiz. Let's just call it a day. Is that okay? So I was so worried I would let people down. I was worried about letting Grace down. Is everybody okay with this? Yeah, I'll hang out, and if you have questions, you can talk to me. Let's call it a day. That 4D stuff just pretty much ends everything. Olivia, my friend, could you just hit stop on that, please? Thank you.